Ooh, where are the students? Where's the? Did I post it in the wrong place? No. I lost my mind. No. Did I join the wrong meeting? Oh, I posted the wrong link. Yeah. All right. God damn it. Okay, they should start trickling in now. Hey guys, sorry about that. My copy paste foo must have slipped up a little bit. I don't know how that happened really, but thank you for double checking and following the correct link. And go back and edit the correct link into the natural place there too. I must have still had that YouTube link in my clipboard. All right, here we go. Okay, hopefully people will start filtering in here. I don't want to like storm ahead without most folks here, so I am going to give a few seconds to start really picking up. But since we are also on a bit of a time crunch, I'm going to come over here and just talk a little bit about the organizational stuff before we dig into the actual mathematics. It's unlikely we're going to finish all 3 sections that are related to the quadratic homework today. Of course, that's not going to happen. So I will be pushing some homeworks back. This is MAC1105, section 7. It's a lecture, and today is the 21st. Just to focus. So today, I'll look a little more absolute value inequalities. And this was associated with, I think, homework 5. My homework 6, it was, yeah. And then we're going to start on quadratic functions. All right. Specifically, the stuff relating to homework 7. Homeworks 8 and 9 we were also planning to do this week, but since we lost so much time on Tuesday, going back and making sure we really understood the regression stuff, we really took our time on that. That's okay. That stuff takes some time. We're probably not going to get to all of homeworks 8 and 9. So this is my goal for today. We're going to wrap up homework 6, which is on absolute value inequalities. That's the thing we haven't done there. If you want to see the introduction to the homework 6 material, you'll have to go back 2 lectures, right, to last Thursday. That's where I first showed you these things. But at the end of that lecture, we didn't get to finish solving examples. I showed you the unpacking rules, showed you all the rules that you need to do the stuff, but I want to make sure you've seen some examples. And then we're gonna start getting into quadratic functions. So I don't want to waste any time. You guys probably don't want me wasting your time. So let's finish homework 6 on absolute values. Specifically the inequalities. Recall the 2 unpacking rules. If you have the absolute value of some shit is less than a constant, this unpacks as the negative version of that constant is less than that shit is less than the positive version of that constant. And it's worth mentioning that if this is a less than or equal to, then these will all be less than or equal to's. And then the other unpacking rule we had was that if you've got the absolute value of some shit is greater than a positive constant, that unpacks into two statements. Either your shit is greater than the positive version of that constant, or your shit is less than the negative version of that constant. And again, if this was a greater than or equal to, these would all be greater than. These would be the weak versions, less than and greater than or equal to. It's worth noting that for all of these, C needs to be positive. To make sense. If you have something like the absolute value of some shit is less than -2, this will always have no solutions. Or whatever, if this is anything over here is negative, this will always have no solutions. Because it's not possible for the absolute value of some shit to ever be negative. And if you're less than -2, that means you're definitely negative. So this sort of thing always has no solutions. And if you've got the absolute value of some shit is greater than a negative constant, this is always true. This would be solved by any numbers you're able to plug into such a statement. So these things are only interesting if the constant C happens to be positive. I'm using the word shit here because you can have any sort of combination of variable things in there. I used to write this as absolute value of f of x is less than C, and people didn't like the function notation. So here just shit can be x plus 5 or 2x minus 7 or anything like that. So these are the rules that we learned last Thursday, but we haven't seen specific examples yet. I want to get into some specific examples. We'll solve 1 or 2 inequalities of each type, and then we're going to move on to talking about quadratics. Feel free to take a screenshot if you haven't gotten this all written down. I am going to go ahead and turn the page in about 5 seconds. All right. So some examples. What if I want to solve the inequality absolute value of 2x minus 1 is less than 4? My first step is going to be to unpack this absolute value inequality. I need to get rid of the absolute value. All right, the absolute value is like an impenetrable box. There's only a few things we can do with it algebra-wise, so the easiest way to work with an absolute value inequality is to rewrite it without the absolute values. So first we unpack. That's why we have those rules. So this will unpack according to that first unpacking rule as -4 is less than 2x minus 1 is less than +4, right? The 2x minus 1, that's my shit. My constant C is 4. So I've got the absolute value of some shit is less than 4. That will unpack as -4 is less than that shit is less than +4. And now these compound inequalities, you can do whatever you want with them. You can treat them just like equations. The only catch is you don't want to multiply or divide through by a negative number. If you find yourself multiplying or dividing through by a negative number, the inequalities flip over. Other than that, they're just like equations. So my goal is to kind of isolate x. I can isolate x in the middle here by adding 1 everywhere. So if I add 1 to all 3 parts of this inequality, I'll have -4 plus 1 is -3 is less than 2x minus 1 plus 1 is 2x is less than 4 plus 1 is 5. So first we add 1 everywhere to get rid of the -1 in the middle. My goal is to just get this to an x. Now I can divide everywhere by 2. And that would give me -3/2 is less than x is less than 5/2. And I've said a few times in this class, one of the things I really want you guys to focus on is getting comfortable with fractions. I know it's not easy. I know we have this fear of fractions. It's a perfectly reasonable fear. Division is a weird operation, but I promise if you follow the rules I show you and put the time in solving these things by hand, lean less on the calculator than you want to. Try to force yourself away from it. You'll build confidence and you'll move faster. So what is this solution then in interval notation? We're done here. We've solved this inequality. You got x alone. It can be helpful to sketch on the number line. So I'll put -3/2 over here. That's -1.5, right? 2 over 2 is 1. So 3 over 2 is 2 over 2 plus 1 over 2, or 1 plus 1/2, or 1.5. So this is -1.5. And in the same way, 5 over 2 is 2.5, right? Because 4 over 2 would be 2. So 5 over 2 is 4 over 2 plus 1 over 2 is 2 plus 1/2. But I'll just mark this over here as 5/2. And this says -3/2 is less than x. So x has to be to the right of -3/2. But at the same time, x has to be smaller than 5/2. So what I'm looking at is the stuff in between. And you can actually compare this to the definition of an open interval, right? This is the exact same thing as the definition of the open interval from -3/2. So we use a parentheses here because this is a strictly less than, meaning x has to be strictly greater than -3/2, or -3/2 has to be strictly less than x. If you plug x equals 3/2 into this portion of the inequality, you don't get a true statement, all right? Because -3/2 is not strictly less than -3/2. And for the same reason, we have to use a paren on the right-hand side here. So here's my solution interval kind of sketched out and shaded on the number line. And if we want to write that in interval notation, the solution set is the open interval from -3/2 to 5/2. And again, I really invite you to take this solution and compare it to the definition of the open interval we used on the very first day of class when we introduced what open intervals were. Not a hard problem, right? 3 little lines, 3 little algebra steps, and then we sketch our solution to make sure we write it down correctly in interval notation. But the notation can look a little bit weird at first, right? Because you've got these multiple inequalities stacked together. And the first few times you see these, they can feel strange. So are there any questions you guys would like to ask about this solution process, or why we write things, or if it would be okay to write things in another way, anything at all? Okay. I'm going to switch then to a different example. Let's try something like the absolute value of 5x plus 3 is greater than or equal to 2. My first step here is also going to be to unpack And since this is an absolute value is greater than constant inequality, rather than absolute value is less than a constant, here I have to use the other unpacking rule. So the other unpacking rule is if you've got the absolute value of some shit is greater than a positive constant, then either that shit is greater than that constant, or that shit is less than the negative version of that constant. And this should make intuitive sense. If you think about what the absolute value function does, I don't know if I've ever seen this before, but I'm going to have to decline that for a moment. Hold on 1 second, fellas. What the hell is this? Okay. Let's get back to it. So we want to unpack this inequality, and we're trying to explain intuitively how you can understand this unpacking rule. How is it possible for the absolute value of something to be larger than 2? Well, what sort of things have an absolute value greater than or equal to 2? Things that are themselves greater than or equal to 2. All right, if you're bigger than positive 2, then your absolute value is going to be bigger than positive 2. Or if you're more negative than negative 2, like negative 3, negative 4, negative 5, all of those have absolute values which are bigger than 2. So if the thing inside the absolute value is to the left of negative 2, that will also give you solutions to this original inequality. So this is the unpacking rule, the second unpacking rule, applied to this inequality. And now we just treat each of these separately. So this first fella, I'd begin by subtracting 3 from both sides. If I subtract 3 from both sides here, I'll get 5x is greater than or equal to negative 1. And over here, if I subtract 3 from both sides, I'll get 5x is less than or equal to negative 5. Yeah, no problem. From there, I can divide both sides by 5 in each of these. And it's good habit to continue writing the word or in between. So if I divide both sides here by 5, I'll get x is greater than or equal to negative 1/5. Or, and if I divide both sides by 5 here, I'll get x is less than or equal to negative 1. And now both of these, we've isolated the x, right? So we've solved both of these inequalities. And since these inequalities together are equivalent to the original inequality, we just have to sketch the solution set here. And having that word or between them can help us remember what to do. The word or is linked to the union symbol. So let me draw a number line. Again, we want to try and get comfy with these fractions. So I'll put negative 1 and negative 1/5. So which one of these, who's bigger, negative 1 or negative 1/5? Which one goes to the left of the other? If I want to put one of them here and the other one here, which one goes on the left?
It'd be negative 1.
Yeah, good. This highlighted bit here would be negative 1. So negative 1/5 is bigger than negative 1. Negative 1 is to the left of negative 1/5. This would be negative 1. This would be negative 1/5. Some people have an easier time thinking in terms of decimals. 1/5 is 0.2. So this is negative 0.2. This is negative 1.0. Now, I need my x's to be greater than or equal to negative 1/5. That's everything to the right of negative 1/5, including negative 1/5 itself. That's from the or equal to part. That tells me to include the negative 1/5. And then this fella says, okay, I'm also kosher if my x's are to the left of less than or equal to -1. So everything less than or equal to -1, that's everything to the left of -1 on the number line. And again, because it's an or equal to, because it's the weak form of the inequality, we use the brackets here. And then you just have to remember that this word or is connected to the union symbol, right? I'm happy with things that come from this set or from this set. So I would like to join those two sets together into a single set. That will be my solution set. So this is going to be -infinity to -1 bracket like this. Remember, we always use the paren on the infinity symbol, unioned with -1/5 to positive infinity. Any questions on this example? So shading the region is what helps with the direction of the bracket or paren, right? So this guy, for example, says x has to be greater than or equal to. The easiest way to remember that is the thing, we're in Gainesville, right? Think of the greater than and less than symbols as like an alligator that eats the bigger guy. So this guy is the alligator eating the bigger guy. This says x has to be greater than or equal to -1/5. Greater than or equal to -1/5, that means you got to be bigger than -1/5. That means you have to be to the right of -1/5. So I shade this, and then my bracket, point like opens to include that set. So this bracket has to open to the right because I'm looking at things that are to the right of -1/5. And similarly over here, x is less than or equal to -1. Again, this eats the bigger guy. So this is saying -1 is the bigger guy, which means x has to be less than -1. So I'm interested in things that are to the left of -1. So the bracket faces the set. Other questions on this one? It's a good questions. Okay, I'm going to do one more example on absolute value inequalities, and then we're going to start talking about quadratic functions. And if you came in a little bit late, I know that there was some confusion with the link, and I'm sorry about that. I am going to extend homeworks 8, 9 to next week because we're not going to get to them, but I'm going to try to get through all the homework 7 content today. But before we do that, one last thing here on absolute value inequalities, just to make sure we're really feeling super comfy. Let's look at 2 minus, how about 2 plus the absolute value of 3 minus x over 5 is less than, well, less than or equal to 7. Okay. So this is not immediately looking like one of our unpacking rules. The absolute value isn't all on his own. If we wanted to, we could make life more complicated by putting a number here, multiplying the whole absolute value that we would have to divide over by, but I just want to give you a feel for what to do with these slightly more complicated ones. I want to isolate the absolute value, then unpack, and then go through the procedures that we just did. Now we're going to have to be a little bit careful here. So first, let's subtract 2 from both sides. That will get my absolute value on its own. So I'd have absolute value of 3 minus x over 5 is less than or equal to 7 minus 2 is 5. Now I'm ready to unpack. And here I've got an absolute value of some shit is less than a positive constant. So I know that that will unpack as one of those compound inequalities, the negative version of my constant is less than or equal to my shit, which is 3 minus x over 5, is less than or equal to the positive version of my constant. So that's the first unpacking rule. Again, my goal is to get x alone in the middle. This time it's going to be a little bit trickier. But if I want to get x alone, I should try to get the x over 5 alone. That's a good goal. And then I'll get rid of the 5. So first, let's get rid of this 3. To get rid of this 3, I'm going to subtract 3 everywhere. Right? This is a positive 3 from which x over 5 is being subtracted. So if I subtract 3 everywhere, negative 5 minus 3 is negative 8. So I'll have negative 8 is less than negative x over 5 is less than or equal to 5 minus 3, which is positive 2. Everybody with me so far? Now here's where something funny is going to happen. Remember I said you can treat inequalities like equations, right? You can add to both sides, you can subtract from both sides, you can multiply on both sides, and you can divide on both sides by any given number. If, however, you multiply or divide by a negative number, and my next step to get x alone, so my step here, I subtracted 3 from both sides. Subtract 3 everywhere. My next step would be to multiply by negative 5 everywhere. And that will make this an x, right? Negative x over 5 times negative 5 is just x. But since I'm multiplying through by a negative, the inequalities are going to flip. When we multiply or divide by a negative number, inequalities flip. So come over here. 8 times 5 is 40. So negative 8 times negative 5 is positive 40. So this will be 40. But since I'm multiplying through an inequality by a negative quantity, the inequality is going to flip. Negative x over 5 times negative 5, that's just x. And 2 times negative 5 is negative 10. And there the inequality flips as well. So this is the flipping of the inequalities that can happen anytime you multiply through by a negative number or divide through by a negative number. So what I end up with is now this statement. 40 is greater than or equal to x is greater than or equal to negative 10. Kind of changes the structure a little bit. But it's still the same sort of thing. And the good news is that this is a very simple way to read the answer. You just have to be a little bit careful. Negative 10 is definitely to the left of 40. So once you get your x isolated here in the middle, just draw the boundaries. And remember to put the smaller guy on the left, the bigger guy on the right, regardless of the order up here. I need my x's to be smaller than 40, right? This says 40 is bigger than x. So I'm interested in things to the left of 40, but I also need x to be bigger than negative 10. So I'm interested in the stuff that's between 40 and negative 10. And because we're using a weak inequality, the or equal to version of these inequalities, we will include the brackets here. We will include the endpoints. So my solution set here is the closed interval from -10 to 40. These are about as bad as these get. If you're comfy with these, you're in good shape. But you want to take the time to make sure you really are comfy with these. I know just getting the chirality right, like greater than versus less than, can be a little tricky, and remembering that it always eats the bigger guy can help. So this says 40 is something related to x, and if you want to know which one it is, just remember that the symbol eats the bigger guy. So this says 40 is bigger than x. And similarly, this says x is something in relation to -10. The inequality always eats the bigger guy, so this says x is bigger than -10. Any questions on this? Okay. So we should be good to finish up the homework on absolute values, their graphs, solving equations, solving inequalities. We've looked at all of that. This inequality stuff, I just wanted to make sure we went back and had enough examples of in class so that you really feel comfortable doing those in the homework. If you do run into any troubles, remember you can come see me in office hours, but I am going to keep the homework for those set with its current due date. I'm not going to push that one back any further. We've had enough time on that. I do want to start on the homework 7 material now, which is all about quadratic functions. So let's get in here, and I think we can just get started by looking at a few problems. I'm sure everybody knows what a quadratic is. I don't want to bore you to death, but I will have to give you the basic definitions. I think before giving you a nice general definition, God damn it. Let's see if Pearson can get its head out of its ass. No, nothing. So just so we're really clear on what is due when, because I know we've changed around some dates. Everything up through homework 6, including this quiz 2, these are going to stay. These are going to stay due on the 26th. Homework 7, this is what we're going to talk about today. This is also going to stay due on the 26th. Homeworks 8, 9, and quiz 3, I will push those to next week. Okay? So I want to make sure you guys are really comfortable with all the material that you need for homework 7. So I'll pop this open. We can look at some of those problems. Before that, I want to give you just a few little introductory things. Your kind of basic quadratic we should kind of begin with is the function f of x equals x squared. Okay, and I do want you getting comfortable with the function notation, f of x instead of y there, helps you understand inputs and outputs. All the other quadratics are some variation on this, right? If you move this left, right, up, down, you stretch it out, or you compress it down, all of those things come from this guy. The big difference between a quadratic function and a linear function is that your variable shows up to the power of 2, right? That's the quad is a Latin prefix meaning 2, quadratic. And this graph you need to know. So let's make a table. Inputs and outputs. If I feed this function -3 as an input, f of -3 is -3 squared, which is +9. If I feed it -2, f of -2 is -2 squared, which is +4. If I feed it -1, -1 squared is +1. If I feed it 0, the square of 0 is 0. If I feed it 1, the square of 1 is 1. If I feed it 2, the square of 2 is 4. If I feed it 3, the square of 3 is 9. And you'll notice some symmetry, right? This is like a palindrome, 9410149. It's symmetric about the 0 here. And you'll notice a corresponding symmetry in the graph. Okay, so we call this -3. -2, -1, 1, 2, 3. I'll mark this up here as 9. I'll make this down here 4. And something like this down here as a 1. So we want to graph these points, -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. And it's kind of looking a little bit like your absolute value in the sense that it like goes down for a bit and then it comes up for a bit, except here things are curvy. All right, these are not straight lines. We're getting steeper and steeper as we go out. So this is our first kind of curvy function. This is our first kind of graph that's not made up of straight lines, which is exciting on its own. So this is what the graph of x squared looks like, and you need to bake this into your head. This is called a parabola. This is the graph f of x equals x squared. This is the x-axis, and the shape is called a parabola. The Greeks knew about these, they studied them, but they studied them a little bit differently. They defined their parabolas in terms of geometric things, distances. So they had a very tricky way of defining these curves that had to do with what they're useful for. These are actually, if you look at a satellite dish, you know, if you go out in your neighborhood, you see anybody who has satellite TV or whatever, those satellite dishes, if you look at them from the side, are actually parabolas. And that's because of their neat geometric properties. If you send a signal in here, it'll always get bounced up to the same place, no matter where it hits. So a special property of these things that the Greeks used to define them, but we usually think of them as graphs of quadratic functions. So all quadratic functions have graphs which are parabolas. And they can be moved around. Like I said, you could lower this thing down, you could shift it left or right, you could move it up, you can stretch it out, you can compress it down, you can stretch it horizontally. All of those are possibilities. This point right here at the bottom where the thing kind of turns around, that's called the vertex. And we'll talk more about that in just a little bit. So before we go any deeper, I just want to give you the definition. A quadratic function is one which can be written in the form f of x equals a times x squared plus b times x plus c, where a, b, and c are constants. Okay. And sometimes it's not super obvious what's a, what's b, and what's c, but a is always the number attached to x squared, B is always the number attached to X, and C is always the constant term floating around without any variable attached. These constants are called coefficients. All right, so the number that is attached to a variable is called the coefficient for that variable. So I would say A is the coefficient of X squared. B is the coefficient of X. Another name for the number A is called the lead coefficient. A is often called the lead coefficient. Later, when we talk about polynomials in greater generality, the term lead coefficient is the coefficient of the largest power of X. But here in the setting of a quadratic, the largest power of X is always 2. So this number A is called the lead coefficient. So let's take a look at a handful of these problems that you guys have. We want to talk about these kind of general properties. Quadratic, we'll talk about this. Okay, we'll talk about finding those numbers, vertex axis symmetry, increasing, decreasing. All right. So, okay, I'll hold here. You may want to take a screenshot. Back up just a little bit, you can get all the good stuff in one spot. Right. This is the start of quadratic functions. If you know the numbers a, b, and c, those tell you everything about the function. So one of the most important things to do at the outset is to get comfy just figuring out what those numbers are. Also, there are some geometric features of parabolas in general that you want to know, just some names of some things. So that's what I'm going to show you next, just the names of those things. And then we'll talk about how to determine the numbers a, b, and c. And then we'll start showing the connections between the numbers a, b, and c and the geometric things. Does anybody need more time to write these? Okay, moving on. I'm going to draw a more general parabola now. I'll draw a few examples. You can have, oh my God, are you serious? Yes, sweetie, I'm teaching right now. What's going on? I can't hear you, but I gotta hang up. I'm teaching. My wife called me. So parabolas always kind of have that same shape. They look like this. The point down here I mentioned a minute ago, that point where they kind of turn around, that's called the vertex. And it's an ordered pair. The x coordinate we call h, and the y coordinate we call k. So this here would be h, this here would be k. I'm worried that something's going on. She knows. Okay. There's symmetry here. Like we said, that first example we looked at, y equals x squared, had that symmetry. And all parabolas have a line of symmetry. We call that the axis of symmetry. And that axis of symmetry always is this vertical line running through the vertex. So you remember from your past algebra classes that vertical lines always have the equation x equals some constant. So this would be the line x equals h, where h is this number from the vertex. Sometimes they have x-intercepts, not always, but sometimes. I'll call this point R1, 0, and I'll call this point R2, 0. Quadratics can have up to 2 x-intercepts. Meaning no more than 2. And I'll give you a formula for those numbers R1 and R2 in terms of the coefficients eventually. Mark, I'm not quite clear on the question you asked in chat. So ax squared plus bx plus c, that's the general form of a quadratic function. Mx plus b is one way of writing a linear function. Yeah, the idea, one of the ideas is making sure you can recognize whether something is linear or quadratic or something else. Right, so right now I'm just showing you these basic geometric features of a parabola. They always have an axis of symmetry, they always have a vertex, and they can have at most 2 x-intercepts. Here's another picture. It's possible for a parabola to open down, and it's also possible for them to have no x-intercepts. Right? So here's another picture of a parabola. Always still a vertex. Still an axis of symmetry. The thing I want to highlight here is that this first guy, he opens up. The second guy, he opens down. And one of the easiest things to figure out, one of the simplest questions we can ask you about these parabolas is based on their equations, or based on the formula for the function. How can you tell if the parabola opens up or opens down? So if A is positive, the parabola opens up. If A is negative, the parabola opens down. And you'll notice this one doesn't have any x-intercepts. This one has 2 x-intercepts. And the very first example we looked at, just good old-fashioned x squared, he had 1 x-intercept. So all of those are possibilities. This guy we would say is decreasing everywhere to the left of h, and then he turns around and is increasing everywhere to the right of h. Because over here we're going downhill, 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 and then we turn around, we're going uphill, uphill, uphill. This fellow is increasing everywhere to the left of h and decreasing everywhere to the right of h. So let's look at a few simple examples here where we're actually trying to do something. So just pictures to get you comfy. You may want to take a screenshot. Okay. So I'm going to tab back over to the homework here, and we'll go ahead and look at one of those earlier questions here. Linear, quadratic. Okay, here, let's determine the numbers. I should have closed that. The coefficients A, B, and C for the functions. I'll do several parts here. F of x equals 2x squared minus 3x plus 7. G of x equals 6x minus 3x squared. And h of x equals x squared minus x. All right. So in this first guy, f of x here, can we find the coefficients a, b, and c? Who can help me out with the coefficient a, the lead coefficient? Yeah, Brooke and Kendra both nailed it. Yep, Matthew. A is 2 here. What about the next coefficient, b? Sometimes we call him the linear coefficient because x to the 1 here is like the linear term. We need to be a little bit careful. Yeah, so this one is -3, right? The minus we might not think as being a part of that coefficient, but it really is. So b here is -3, and c is going to be +7. So remember, the formula that we're looking at is ax squared plus bx plus c. So if there is a minus sign attached to one of these guys, that really is a part of the coefficient. G of x is a little trickier. Who can help me out with a in g of x? What is the lead coefficient? Yeah, excellent. Here it's -3. Yeah, here a will be -3. What about b? Good, yeah, Mark's got it. B here is going to be 6. And C is 0. And it might be useful to rewrite this guy as -3x squared plus 6x plus 0 to really convince yourself that this is the same as this and that these numbers are correct. What about in h of x? What is a, what is b, and what is c here? Yeah, so the number in front of x squared, we don't see a number there, but that means that that's a 1, right? Just like 5 is 5 times 1, x squared is x squared times 1. So the number a here is 1. You've got a minus x here. This minus tells you that the coefficient will be negative, and because you don't see anything written there, you know that that's a -1. And then c again is 0. Let's do one more thing like this. I'll call this guy P of x. Let's make him 4 minus 16x squared. What are the numbers a, b, and c here? Yeah, so a here is negative 16. That's the number that's attached to the x squared. B, good, yeah, b here is 0, right? There, we don't see any x term at all, which means he's hiding. And the way he hides is by having a coefficient of 0, and then c is positive 4. So if I wanted to write this in standard form, it would be negative 16x squared plus 0x plus 4. And there we can see A, B, and C. All right. This is a good place to get started, but I do want to talk a little bit more. So let's dig back into some of these homework problems and see some of the slightly more challenging things we can do. We're going to learn how to factor these. We're going to learn how to graph them. I think the next sort of thing that I would like you guys to work on is figuring out the vertex, right? So they've got plenty of questions asking to find axes of symmetries, vertices, where we're increasing, where we're decreasing. Goodness, yeah, we're just trying to preview. That's fine. This is fine. Let's do something like this. So I'll copy this graph down. It's going to be a rough sketch, but this is coming from homework 7. That is problem 6. We have the graph of some quadratic function here. This is 1, and up here is 3. And it's not really clear where those are, so we don't need to worry too much. Okay, they want us to say the sign of the lead coefficient find the vertex, state the axis of symmetry, and also discuss intervals of increase and decrease. That's something we haven't gotten a lot of practice with. And then domain and range. Okay. So here's our graph. What is the sign of the lead coefficient? Remember, the number A is the lead coefficient. And remember, sign just means positive or negative. So what is the sign of the lead coefficient for this parabola, for this quadratic? How do we tell? So remember what we said here. Oh, shit, other way. We said if the lead coefficient is positive, then the parabola opens up like this. If the lead coefficient is negative, then the parabola opens down like this. Is this parabola opening up or down? Yeah, this guy's opening down, right? If this is like a big old mouth, It's eating downward. So the sign of the lead coefficient has to be negative, yeah. So I'll put the answers in here in a different color. Another way to say negative is less than 0. By the way, you'll encounter those two different ways of saying that. Okay, where is my vertex? Or what is the vertex here? So the x value is 1, and the y value is 3. So the vertex, we like to give that as an ordered pair. It's 1, 3. In other words, h is 1, and k is equal to 3. Right, this point right here is the ordered pair 1, 3. And remember, the x value of the vertex, we always call that h. The y value of the vertex, we always call that k. What is the axis of symmetry? We need to be careful here. The axis of symmetry is a line. So it's not just a number, it has an equation. What is the equation of this line? Good, x equals 1, right? Vertical lines are always x equals a constant. Horizontal lines are always y equals a constant. So my axis of symmetry here is the vertical line, x equals 1. Now, intervals of increase and decrease, these are more fun. We did talk about these once before when we talked about absolute value graphs. We talked about finding intervals of increase and decrease. Who remembers the trick to getting these questions right? There's some very, very important warning attached to these questions. The answers are always formatted in a certain way. When you want to describe intervals of increase and decrease, how do we always give these answers? It's true in interval notation, but more specifically, open intervals of x values. It would not be correct to say that this function is increasing from negative infinity to 3 and decreasing from 3 to negative infinity. That would be very wrong. What is correct here is to say that this function is increasing from negative infinity up to 1. So we are increasing everywhere over here. And we are decreasing everywhere over here. So this is a very common sticking point. And every semester we end up taking off a bunch of points for people who make this mistake. When I ask you where is a function increasing or decreasing, you need to tell me the open intervals of x values, not points, not y values. If you find yourself reporting any y values, something has gone wrong. I think we would all have no trouble saying this is the part of the graph that is increasing, and this is the part of the graph that is decreasing. But how you describe it, the notation you use to describe it, is really important because there's ambiguity if you do it any other way. So if I'm walking along the graph from left to right, over here, everywhere I'm going uphill, and over here, everywhere I would be going downhill. So yeah, this is the increasing part, and this is the decreasing part. But you need to give the answers in terms of the inputs. So remember, this is 1 right here. So on what interval is this function increasing? What is this interval here? The interval of x values, the open interval of x values for which this function is increasing. Very good. Yeah, Kendra nailed it. Thank you, Kendra. From -infinity up to 1. Remember, only x values. I don't give a shit about the y values. I don't want any information about the y values. Intervals of increase and decrease are always given as open intervals of x values. So this 3 doesn't play a role. I care about the x values only. So from -infinity up to 1, that is where we are increasing. And where are we decreasing? Yeah, excellent. From 1 to infinity. Any questions on this, the increasing, decreasing stuff? It's very easy to get confused with points and y values. The trick here is, remember, just intervals of x values, open intervals of x values. Okay, let's talk domain and range. What's the domain of this graph? If I imagine these arrows go on and on forever in both of these directions, this graph keeps going out like this, and I switch everything onto the x-axis, what is my domain? Yeah, the domain here is -infinity to infinity. Maybe I'll show you in Desmos something really quickly if we're having a hard time conceptualizing this. This is so silly. Right. So here's a parabola looking an awful lot like my parabola. Right? It has that vertex at 3, 1, and it opens down. This one's a little bit different than ours, but close enough for jazz. If you zoom out and out and out, you have to imagine smooshing this whole graph down onto the x-axis. And it dives down really quickly, but if you zoom out far enough, you'll find an x value on that graph that is -30. You'll find an x value on that graph that is -50, 80, 100. You know, we can come way, way out. This thing does eventually reach over as far as you want. The domain here really is all real numbers. It's not super obvious from the picture because you only see a small portion of the x values on the graph at any given time. But this parabola does reach out infinitely wide. It just goes down much faster than it goes out. The same is true for our guy. If you were to smush this graph down onto the x-axis, everybody would get hit. Our domain is all real numbers, or the open interval from -infinity to infinity. And this is true for all quadratic functions, right? For all polynomials, in fact. The range, though, that's a little more complicated. Can somebody help me with the range of this function? Yeah, Logan's correct. Care to explain that a little bit, Logan? Why is the range negative infinity to 3? It's correct. But why?
Because the vertex stops at 3 on the y-axis, so it can't be anything above that.
Good, yeah, we're looking for an interval of y values when we want to find the range. I want to know what are all the y values on the graph. And if you imagine coming in here with your hydraulic press and smooshing this whole graph down onto the y-axis, this point would get smooshed here. This point would get smooshed here. Everybody below 3 on the y-axis is going to get hit. And 3 itself does get hit, right? So the range here is negative infinity up to and including positive 3. So these are the basics of quadratic functions. We can look at one more problem quickly. Let's dig a little bit deeper in here to find something a little harder. So we want to find the maximum y value on this graph. To do this, we're going to need our formula for the vertex. So let me go ahead and show you this last formula you need for this homework. And then we'll come back and answer this question. So you have already the standard form. For a quadratic. This is ax squared plus bx plus c. There is another form. There's actually two other forms we're going to talk about. And the first other one we're going to talk about is the vertex form. This is x minus h squared plus k. And then over here, there's the number a. And the number a here is the same as the number a here. H here is the x coordinate of the vertex. And k here is the y coordinate of the vertex. There's a formula for the number h, and I'm going to show you where this comes from after we talk about the quadratic formula. So to find h, that's always going to be negative b over 2a, the numbers from the standard form. And then if I call these f of x, k is always f of h. So if you're given something in standard form and you want to find the vertex form, first you find h using this formula, and then you find k by plugging h into the function. So let me show you what that looks like. We'll come back here to this particular problem. We've got negative x squared plus 6x plus 6. So I want to write this guy, which is in standard form right now, in vertex form. So these this vertex form thing, this is important. Make sure this is somewhere in your notes nice and clear that you can refer back to it. We'll need it often. Our first step is going to be to find H. So we know, I'll write down what A, B, and C are. A is -1, B is +6, and C is also +6. So to find H, use the formula. H equals -B over 2A, which is the negative of B, that's -6, divided by 2 times A, which is -1. So that's -6 over -2, which is +3. Now to find K, we plug X equals H equals, which is 3. So K is always f of H, which in this case is f of 3. F of 3 is the negative of 3 squared plus 6 times 3 plus 6. So 3 squared is 9. The negative of that is -9 plus 6 times 3 is 18 plus 6. So we'll continue this up here. -9 plus +18, that's +9. +9 plus 6 is 15. So K is f of H, which was f of 3, which we said was 9 plus 6 is 15. So our vertex is the point 3, 15. And now we know how to write this thing in vertex form, right? Because to write down the thing in vertex form, all you need are the numbers A, H, and K. H and K are the coordinates for the vertex, and A is always the same as A in standard form. So A was -1. And f of x in vertex form must be f of x equals -1 times x minus h, that's x minus 3 squared, plus k. So this piece is A, this piece is H, oh, sorry, K, 15. K is 15 here. And this piece is K. All right. So I think this is about where we're going to run out of time for today. Yeah, we're actually a little bit over time. I appreciate you guys being patient with me these last 4 minutes. I will have homework 7 coming due this week. You should be able to handle everything in here. If you do run into any trouble, of course, you can come by and visit me in office hours. If you have any problem that's giving you a hard time or anything that's bugging you, I'd be happy to spend some time working on it with you in private or in a group office hour if you feel more comfortable there. Please work hard to finish up everything through homework 7. And then homeworks 8, 9, and quiz 3, I will push those down a little bit. But everything up through homework 7 needs to be done by the 26th. That is it. So I hope you guys have a lovely rest of your day. And again, if you do need help with anything, come by an office hour or send me an email with a picture of your work. If you do email me, I want to say this, if you do email or Canvas mention me, please include the class that you're in, say college algebra. That way I know where to look because I do teach other classes. So thank you. And that is it. Any last minute questions before we go? Alrighty then, I'll go ahead and end the meeting here. I hope you guys have a great rest of your day.